Hello everyone, I'm Shiqi Jiang from Microsoft. I'm very happy to have this opportunity to present our work, Flexible High-Resolution Object Detection on Edge Devices with Tunable Latency. This is a joint work with my colleagues Zhiqi Lin, Yuanchao Shu, and our collaborators Yuanchun Li and Professor Winxin Liu from Tsinghua University. As we know, people are deploying cameras for video analytics at scales, for public safety, business operations, traffic planning, and so on. Recent years, with the rapid growth of deep learning techniques and hardware accelerations, a number of DNN-based video analytics approaches are proposed, and they have achieved excellent performance. During the engineering practice, people noticed that rather than running tasks on cloud, running on edge, like a smart camera, may provide several key benefits, including easier deployment, lower price, higher availability, and better privacy. However, DNN is usually computation intensive, but edge compute is provisioned with limited resources, so posing significant challenges on running such neural networks. This tension is even worsened by the ever-growing video quality from high-resolution cameras. Today, most smart cameras are equipped with 4K or even 8K cameras. High-resolution cameras can provide smoother and more detailed images, but also require large models to process, which is not affordable for edge devices. To fill this gap, we have some explorations. We made a framework for object detection tasks, which is a fundamental building block of many video analytics applications. The framework is on 4K videos and with various hardware platforms. We can achieve up to 8 times speed up and 65% accuracy improvement compared to SOTA models. What's more, this framework provides a feature we named Tunable Latency. That means given any latency budget on any hardware, we can always best utilize the resources and achieve best accuracy within the constraints. So next, we will introduce how we achieve this. But before that, let's see why existing approaches failed first. We conduct measurements on popular object detection models with different capacities on a public 4K dataset. Currently, most of models are designed for low resolution. So, to handle 4K inputs, generally we have 3 methods. First, we can downsample the inputs. It leads to very low accuracy, shown here. It is because the objects are too small to be detected. In another way, we can scale up models to handle 4K image directly. The blue line represents a series of models named efficient DAT. They have similar structures but with different sizes. With model size increase, their latency increase exponentially. D7, the input is around 2K and its latency is about 2 seconds already. If we continue to upscale it into 4K, its latency is not affordable. Recently, people are also seeking to use uniform partitioning. It divides the image into equal pieces and processes each piece using the same model. As shown in here, the uniform partition results in better accuracy but even higher latency. In our measurements, we also mirror the detection accuracy on different sizes of objects, like small, medium, and large. We have 2 observations. First, Tiny models also have good performance on large objects, shown here, even close to huge models. Secondly, and more importantly, the marginal accuracy gain from different models varies across object sizes. For example, the model D6 is larger than D3. It requires about 6 times more compute power, shown in the figure. If putting these compute power on medium objects, we can get 1.6 times accuracy improvement. But if putting on large objects, the gain is only about 10%. These observations motivate us. We should carefully distribute the limited compute power across the whole image. So here is our key idea. We don't design another new model, but explore existing diverse models. Common CNN treat every pixel equally, and the compute power is distributed uniformly. But we want to prioritize regions and distribute compute power adaptively. Assign a proper model to each region. This feature shows our idea. It is a typical object detection scenario. The blue block contains many people, and they are small. We can apply a large model to detect, to guarantee its accuracy. The green blocks contains a few people. They are large. It is enough for us to apply a medium or even small model to detect. For the red, there are no objects now. We can skip them to speed up. In this way, we can best balance the detection accuracy and the inference latency. What's more, by adjusting the partition plines, we can provide the tunable performance. To make our idea come true, particularly, there are two challenges. First, it is non-trivial to get ideal partition plines. Second, only considering long-term distribution is not enough. We should also handle short-term dynamics in video contents as well. For example, some blocks may turn to empty, and in some empty blocks, objects may appear unexpectedly. To this end, we present Remix. Remix consists of two key modules, adaptive partition and selective execution, to address the challenges accordingly. In the adaptive partition, in the offline phase, we analyze the object distribution and the model capacities. Then we try to generate proper partition plines according to the latency budget. Then the plines are deployed on the edge. So in the runtime phase, the selective execution would determine which block can be skipped, best balancing the latency and accuracy. Next, we will give more design details for each module. In the adaptive partition, the goal is to obtain best partition plines according to the given latency budget. We first profile the diverse models, get their latency and accuracy on different sizes of objects via NN profiler. Then, we analyze some historical frames. By using the ground truth or an oracle model, we can get the object distribution. More specifically, where objects train to locate and what size of them. In this way, given a block of image and an assigned model, we try to estimate the expected accuracy and latency. Based on that, we enumerate every possible partition plines. According to the estimation and the given latency budget, we pick the plines with best accuracy within the budget. The red feature shows an example of generate partition plines. We also design some sub-modules to make our system robust. On the edge, the partition plines are deployed. Here, we try to determine which blocks can be skipped considering short-term dynamics. To achieve this, we present a closed-loop controller. We use previous detection as feedback. We apply an exploration and exploitation strategy. We want to our system behave in the following way. For a block, if objects are detected in previous frames, we do not skip it. If objects are not detected in several frames in a block, we will skip it. For skipped blocks, we also randomly bring some back to check if objects appears again. Since some blocks are skipped, the total inference latency is less than the latency budget. That means there is some compute power left. So we also propose another controller to help adjust partition plans to fully utilize the compute power and further improve detection accuracy. Here is a live demo of our whole system. The label at the upper left is the model used in the corresponding block. The red mask stands for the skipped blocks. The different color represents different partition plans. Here comes the evaluations. We evaluated remakes on public dataset and our own collected videos. Compared to SOTA approaches, remix can get up to 8 times speed up when achieving close accuracy. When under similar latency constraints, remix can also improve the detection by 65% on average. We also evaluate remix on different edge platforms, including NVIDIA Jetson, Karen, and Snapdragon. The results show remix can bring promising inference speed up and detection accuracy gains. We evaluate the performance across scenes. Here, we demonstrate 3 typical scenes: a Plaza Square, sports ground, and street. Compared to Plaza Square, remix perform better on the other 2 scenes because they have much more clear spatial patterns. But we also notice that even in Plaza Square, remix also can perform better than SOTA approaches. The reason is that there are still a lot of irrelevant backgrounds, which provide the sparsity, making rooms for remix. We also evaluate the overhead of remix. Remix utilizes both CPU and mobile GPU. According to our evaluation on NVIDIA Jetson, the average power is about 12 watts. The mobile GPU consumes the majority of power, about 10.6 watts. Remix introduces a pre-processing overhead, where it partitions and resizes image blocks. According to our evaluation, the average overhead of pre-processing is about 112 milliseconds. In addition, the pre-processing is performed on CPU, and the inference is performed on GPU. We pipeline the pre-processing and inference. Therefore, most of the overhead can be hidden. Okay, let me conclude our work. In this work, we propose remix, a flexible high-resolution object detection framework for edge devices. The key idea of remix is to distribute the limited compute resources across the whole input adaptively. Remix is a cloud and edge co-design. We leverage the cloud to analyze massive data to obtain the long-term object distribution, while on edge, we propose efficient closed-loop controllers to handle short-term dynamics in real time. Remix provides the feature named Tunable Latency, which we believe is important towards elastic edge AI. In addition, we are still improving remix. Now, we had added several new supports, including auto partition plan updating, the heterogeneous processing unit utilization, which make Remix even better. Okay, that's all. Thank you.